The next topic we're going to talk about is boiling and melting points and how we can determine these. Now, the first thing that I want to make sure that you understand is that first, you don't need to be able to estimate numbers of boiling points and melting points for substances. But what you will be asked to do is, if you're given a certain group of different compounds, that using your knowledge of intermolecular forces, you can estimate or rank what the boiling points are. In other words, which one would have the highest boiling point, and then the next highest, and so on. And you could rank them from highest boiling point to lowest boiling point, or highest melting point to highest melting, or lowest melting point. So that's all that we're really doing here with this. And so a couple of things to point out. First of all, when we boil or melt something, what we're doing is we're breaking the intermolecular forces that hold those molecules together. We aren't physically taking a particular molecule and breaking those atoms apart. We are not doing that when we boil something. And this is a common mistake that kids make, is they think, okay, well, we're separating the hydrogens from the oxygens. That's not what's happening. What's happening with this is, if I take this water molecule, for example, this water molecule is polar. It has London dispersion forces because it's got electrons. Because it's polar, it has dipole-dipole. And because it has a hydrogen attached to an oxygen, it's got hydrogen bonding. And so this water molecule will form 3 intermolecular forces with other water molecules. Now, they're fairly weak attractions, all of them, but I did give you a ranking in our last video as to which ones are strongest and which ones are weakest. The fact that this has to break all 3 of these bonds in order to boil it is what causes water to have such a high boiling point, even though it's a very small molecule. And so that's what happens when we boil things, is when we boil stuff, we are breaking these interactions so that there is no attraction between this water molecule to this one. When we boil it, we make it a gas. The space between those molecules becomes much larger, and at that distance, you can't form any intermolecular forces. But in order to get those molecules away from each other, you've got to break those attractions, and that takes energy. And so that's what this is all about. The more intermolecular forces that a molecule will have or form with other molecules, the higher or the more amount of energy that's needed in order to boil or melt that substance. And when you boil and melt them, that's what you're doing, is you're breaking those attractions. So if we take a look at this example right here, I've got 6 substances, and I don't have boiling points for them listed on the board, but I do want to rank them from highest boiling point to lowest boiling point. So the first thing that you want to look for when you're given a list like this is you want to look for a substance that is ionic, if there is one. And for this one right here, this guy is an ionic compound. And what you just need to know is that all ionic compounds will have a very, very high boiling point and melting point. And it's because, if you remember earlier on in the unit when we talked about crystal lattices, ionic compounds form crystal lattices. And in order to melt and boil ionic compounds, you've got to break those crystal lattice attractions up, and they're very, very strong. And so compared to any other molecular compound, these will have the highest boiling point and melting point. You'll never be given a list where you have to compare 2 ionic compounds, because that would, for the scope of this class, not be a realistic thing that I would ask. But do identify, if there is one in the list, that it's ionic and that it will have the highest boiling and melting point out of the list. So this guy would be number 1. So now what we're looking for is numbers 2 through 5 for the rest. And the way that we want to do that is we want to identify which ones have which intermolecular forces. So I'm going to go through each one of these and identify whether they're polar or not polar first. And once I've done that, then I can identify what intermolecular forces they have. So first of all, I know that all molecules have London dispersion forces. So I can write those in. The next thing is which ones are polar. So looking at the molecules, and you can draw these out if you want to determine whether what I'm telling you is true or not, and you want to verify what I'm saying. Hydrochloric acid, water, and acetic acid or vinegar are all polar molecules. And so because they're polar, all three of those are also going to have dipole-dipole. Now the last one is which ones have hydrogen bonding. And this one, again, you may have to draw out in order to identify which ones have hydrogen bonding and which ones don't. Remember that hydrogen bonding is only found in molecules that have a hydrogen directly bound to a nitrogen, oxygen, or fluorine atom in the molecule. So hydrochloric acid does not fit that description, so it does not have hydrogen bonding. H2O does have hydrogen bonding. We've established that already. And we also know that acetic acid or vinegar has hydrogen bonding. These ones here, this one has hydrogen, but again, doesn't fit the description of hydrogen bonding, so it doesn't have it. And fluorine, yes, it contains fluorine, but doesn't contain hydrogen. And so then we don't have a hydrogen bonded to the fluorine, therefore no hydrogen bonding for fluorine either. So now once I've got this list and I've got it all set up, the ones that have the highest number of intermolecular forces are the ones that are going to have the highest boiling point. But you can see here that there's a tie between water and vinegar. They both have all three intermolecular forces. So what's the tiebreaker? The tiebreaker is actually London dispersion forces. If you remember from the previous video, I said that London dispersion force strength varies by how many electrons, total number of electrons, a particular molecule will have. So if you look at each one of these molecules, you can see clearly that acetic acid is going to have way more electrons than water is. And so we would expect acetic acid's melting and boiling point to be higher than water. And I'm not going to write the numbers down right now, but acetic acid does in fact have a higher boiling point than water. And it's for this reason. The London dispersion force in acetic acid is stronger than it is in water. So acetic acid is our number 2, and water is our number 3 on our list of highest boiling points. The next one is clearly going to be hydrochloric acid, because it's the only one that has London dispersion force and dipole-dipole of the 3 that are remaining. And then between these two substances left, C2H6 and F2, both of these have just London dispersion forces. So again, when you go to break the tie, you use London dispersion forces to determine which one is going to have a higher boiling point. Clearly C2H6 is going to have more electrons than F2, and so this one is going to be our number 5, and this one will be number 6. And so once you can rank these and identify which ones have what intermolecular forces, then you understand boiling and melting points pretty well, and you should be fine.